jointly organized by the FedMS and ACECC.
Moderator.
And I'm Seunghak Lee from KSC, currently serving as the Chair of Planning Committee ACECC, the Asian Civil Engineering Coordinating Council. Well, this is the fourth session following the previous three meetings. And in this session, we have invited 4 experts in the field of earthquake engineering from different member societies of ACECC, including ASC, JSC, Hockey, and Engineering New Zealand. So without more additional introduction, let me quickly start the session right away by inviting the first speaker of the session. The first speaker of the session is the Dr. Ertugrul Taciroglu, who is a professor in Civil and Environmental Engineering Department in University of California, Los Angeles, from ASC. So the Professor Taciroglu currently working on the disciplines of theoretical and applied mechanics and structural and geotechnical earthquake engineering. He is currently conducting projects on regional performance-based risk assessment of civil infrastructure, structural health and performance monitoring, and soil structure interactions. So please welcome and give him a big applause for his presentation today. Yes, Professor Taciroglu.
Hello, everyone. Thank you, Seunghak. Can everyone hear me?
Yes, very good.
And see my slides?
I can see that.
Okay, great. So I want to talk to you today about simulation and data-driven approaches to regional seismic risk and resilience assessment. And as Seunghak mentioned, I am Ertugrul Taciroglu. My name is a little bit difficult to pronounce, so people call me ET using my initials. I'm a professor in the Civil and Environmental Engineering Department at UCLA, and I also am a faculty affiliate at the Garrick Institute for the Risk Sciences at the same institution. And I'm happy to be here presenting you our work at UCLA. I have many collaborators from many different countries helping all of this work, so I'd like to begin by acknowledging them. So here's a map for my presentation. I want to talk to you about hazards engineering in general. What are the fundamental aspects and elements of doing hazards engineering? And this applies not only to earthquakes, but also other hazards like hurricanes, wildfires, you name it. Then I'm going to be specializing in the methods and tools that we use for seismic hazard engineering. I'll talk about the domain knowledge that we need for this and typical workflows to do what we need to do as engineers, and some of the aspects of the high-performance computing tools and machine learning algorithms we're using to be able to do these tasks at regional scales. Finally, I'll show you some examples of earthquakes evaluated for the city of Istanbul in Turkey, which is a large metropolitan area, as well as my location of Southern California. So here's the basics of natural hazard risk assessment, whatever the hazard is. And it has basically 3 main elements. One is, what are your assets in the region? So by that, I mean not only knowing what the various basic attributes of these hazard, assets are, but what are the pieces of knowledge and metadata with which I can create analysis models of these assets so that I can predict their responses under probable earthquakes, for example. So number 1, what are our assets in the region? Number 2 piece of knowledge is, what is the hazard? And by that, I mean, for example, for earthquakes, what is the probability of having a certain earthquake magnitude or larger earthquakes at a given location in our region? So that's the hazard. And of course, there will be some of our assets that are exposed to hazards, and their specific locations will change the level of hazard that they're exposed to. So not every asset will have the same level of exposure to the hazard. So, and among those hazards, which is among those assets that are exposed to the hazard, which is the intersection of the first two sets, there will be some that will be vulnerable. Maybe not all of your assets are vulnerable. They're properly designed and they're going to be safe and secure after an event, but there will be some that are vulnerable. And then as engineers, our objective is to determine what is those subset of assets that are vulnerable and exposed to the hazard. This is not always an easy question to answer because sometimes assets are interconnected, road networks, power networks, water distribution, etc. And then maybe some elements of your distributed network is exposed to the hazard and they get damaged, but their damage will influence service to even remote locations. So this last piece is also not a very straightforward thing to answer. So why do we need to do these hazards engineering? And what are the three different stages of it? One, the first stage is pre-event risk assessment. Before any event happens, there are certain things that you want to do. This hazard is present in your region and earthquakes will happen. So what do you need to do before any event happens? So you do your studies so that you can do emergency response planning in case an event happens. You will need to know how many people and personnel and vehicles you might need, what kind of equipment, what is the number of population and human beings you're going to have to serve and address issues for. This kind of study will also help you do government policy guidance, as well as the important tasks of mitigation, pre-event mitigation, and insurance planning. What are my vulnerable buildings? How do I strengthen them? And what are the insurance premiums that I have to set aside so that when and if this event happens, which is always the case, then do I have enough money and reserves to start recovering? During the event, this is the second stage, you have to do rapid post-event damage assessment. When I say rapid, because this is perishable data and things are happening quickly and you're trying to recover quickly, this task has to be done rapidly within days, weeks, maybe months, but not beyond that. And so in that realm, doing the engineering studies and assessment studies will help you do emergency response management. You can also learn from your mistakes and successes because you will see what worked in the field and what didn't. And then by observing the damage data from the field, you can develop real life empirical fragility models of your assets. And also you can test whether your predictive models that you've used in the past before the earthquakes actually worked or not. Are they accurate enough? So you can do validation studies with the observations you're making during the event. Finally, in the last stage after the event, you're going to try and do recovery and rebuilding. And then now you want to do these kinds of simulations and analyses so that you can improve your resilience. And this is typically the best opportune time for doing so because before the events, unfortunately, we are not necessarily tuned to as societies to do the necessary actions. But right after people are mobilized, there's more interest and an urgent need to address these issues so you can do your resilience work, whether to find vulnerable buildings in other exposed regions and starting some retrofitting programs or putting aside some more money to do more research to fill in your knowledge gaps. And also then right after the event, if you're observing and doing studies, you have a capability of understanding now or quantifying the post-event downstream effects on human beings as a society, as well as local and regional economies. So what are the typical workflows to do all of these three types of studies? And they, again, come in three pieces. One is you need to build a model of your assets at regional scales. Where are my buildings? Where are my dams? Power lines, all of these things that are exposed to this hazard. And then you need to be able to create models of these assets so that you can do analysis. So that's element number one, asset models. And I'll talk about how to generate asset models at regional scales a little bit later. The other element is determining the hazard at a given location. What, again, is the probability of having an earthquake magnitude or a larger magnitude at a given location? If you know these probabilities, then you can design accordingly, right? So this is the hazard characterization portion. Once you have a characterization of the expected hazard, what is the probable earthquakes in this particular location of my buildings or my city? And once I have the asset models, I can combine them and do some analyses. These analyses is what civil and structural engineers do, for example, and they yield essentially what we call fragility curves Fragility curves that you can see on the bottom right-hand side of this slide are the curves that tell you the probability of, for example, experiencing a collapse given a certain magnitude earthquake. If you have this information for every building or classes of buildings in your region, then you can do analyses like estimate losses, downtimes, repair costs, retrofit costs, etc. And with all of this information, you can do all those types of studies that I mentioned earlier. So let me just dive a little bit deeper into hazard characterization. In places like the United States and Japan, where earthquakes are relatively more frequent, and there are ground stations that have been observing these earthquakes for many years, like 80 years in the United States, for example, it is possible to generate data-driven models to obtain earthquake probabilities. We call these models ground motion prediction equations. There are ground motion prediction equations, for example, for my region of Southern California. And you can use these things to create these so-called hazard curves. But not all portions of the world have frequent earthquakes and or have many years or decades of data to construct such ground motion prediction equations. And there we can do physics-based ground motion simulations, where we can simulate a fault rupture, simulate the propagating waves into our region, and assess the damages it may cause. And this is used even in places like United States, where we have, for example, the Cascadia zone in Northwestern United States, for which we don't have as much data. And also for these regions, we want to have more accurate information, time series, that's we're using physics-based simulations. So the physics-based hazard characterization simulation starts with modeling the source. What is the fault rupture? How much displacement you're expecting at that fault? And then simulating the waves that will propagate through the region. And for that, we have various tools that we run on supercomputers, such as Hercules 2 or EQSIM. And once we have these ground motions across an entire region, we can apply them to asset models. And we create these asset models using multiple tools that we also created in collaboration with our colleagues like Brails++ or Fortuna. And then we can do analysis at each building and determine what their probabilities of collapse are. So here's an example of us using the Hercules tool to simulate a magnitude 7 earthquake in the Aegean region of Turkey in the Mediterranean, and its effects on a nearby city of Izmir. For these simulations, we are using supercomputers and doing very large simulations that run on several hours on these large supercomputers to obtain all of the seismic hazards in that region. So here's an application of this workflow in a general sense to, say, earthquakes in the city of Istanbul. Istanbul is located in the western end of the northern Anatolian fault, which has been creeping over the years and causing many, many earthquakes along its path. And Istanbul is directly exposed to it, and it's the largest city of the country and a heartland for the economy. So any kind of damages will cause large losses of human life and the economy. So it's very important for this country. The only problem here is that this fault doesn't create many small earthquakes or mini earthquakes. So generating data-driven models is very difficult. So we have to use seismic earthquake simulations. So we have carried out very large physics-based three-dimensional simulations for the city of Istanbul, for this very dense portion of Istanbul. And then using those simulated ground motions, we have done an analysis of the probabilities of damage and collapse into a certain building stock within the city of Istanbul. We were able to do so because we knew the ground characteristics of the region obtained from the municipality of the city, where they have done many boreholes and obtained geological data with which we could create our models. And then we have simulated 50 to 60 earthquakes, probable earthquakes in this region, to understand, what kinds of earthquakes might happen. Again, these are very, very large simulations, very fine detailed simulations that we run on supercomputers with billions of degrees of freedom. This is a technology that's available and that can be applied to different portions of the world, provided that some geological data is available. And then once we obtain these ground motions affecting the region, we focused on different clusters of neighborhoods This is one neighborhood in that city called the Zeytinburnu district. And we've created models of 16,000 approximate buildings in the region by using computer vision tools and some heuristic models. And then we've analyzed the responses of each of these 16,000 buildings to 60 different types of earthquakes to obtain their probabilities of collapse if these earthquakes have happened. And these analyses of individual building models under these 50, 60 scenario earthquakes were done again on supercomputers. And if you've done any supercomputing, you would know that this is a very scalable type of calculation. Each analysis of each building can be done independently. So if you have a very large supercomputer, you can actually do this in a very reasonable amount of time within a few hours, etc. So for this particular case, we have done an analysis of 1 million 1 million individual, almost finite element analyses of nonlinear analysis of these buildings. And we've obtained these so-called engineering demand parameters, like what is the maximum interstory drifts that are going to experience. And this information tells us what is the probability of collapse. So we could create fragility curves and probabilities of collapse maps, and we could communicate these to the government, and then they can understand which buildings are the most vulnerable and what kinds of emergency responses they need to do, what kind of mitigation studies they need to look at. I'm skipping some of the details, but we've published this work, and if anybody's interested in the details of it, of course, I can provide you more information. And these 16,000 building models are fairly accurate, but not accurate to the point of being almost a digital twin. But we also have those capabilities of creating digital twins, very, very detailed models of buildings individually and analyzing them individually under earthquakes as well. We can inject the regional simulations into a local finite element analysis box and do sophisticated analysis involving soil structure interaction. You're seeing a hospital building that's a braced steel frame that is base isolated, sitting on top of some soft soils, and we can analyze the response of these individual structures as well. So how do you generate regional asset models? How do you generate like 15, 16,000 building models? So I'm going to give you examples of work that we have done in Southern California on bridges. But we have also done stuff for buildings, as you've seen, but I'll kind of give you a more detailed the description of what we've done for bridges. Bridges are nice because you drive under them, over them. They have many pictures. And so you can, they're amenable to generating automated generation of models, analysis models, structural analysis models, using machine learning tools and other techniques, photogrammetry. So we've extracted some information from national and state databases, which is incomplete information. They're never enough to create detailed models. And there are things that are not quite visible, like reinforcement ratios and some of the structural details. But those are available in structural design guidelines of the state of California and the United States in general. So once you know some basic metadata, year built, et cetera, you can estimate and back calculate some of the other information from these design guidelines. Finally, you can combine that information with information you're observing from satellites and street view images, and you can create detailed models of these bridges. Again, I'm not going to go over the details of our workflows to generate these bridges, but it starts with satellite imagery. We identify the bridge spines, and then we go to street view image resources and extract all the images that see this bridge from its deck and from below. We combine them, do some machine learning and photogrammetry, and identify their attributes with which we can create detailed models of these structures. Here's an example. This is the Colton interchange. It's a curved large bridge that is actually crossing over a fault line, and our Department of Transportation, Caltrans, was interested in us creating a model for it, so they gave us the structural drawings. We've created automated models of this bridge, and we compared it with the model we generated from structural drawings to see how accurate we can get from just image-based models. Even if you look at this bridge's photographs with your human eye, you may get confused as to which column belongs to this bridge, etc. But our automated algorithms can extract thousands of images automatically and identify all of this information. Again, we start with the top satellite imagery. We extract the bridge deck elevation and elevation under the bridge of the surface so we can get freestanding column heights. Using photographs and machine learning algorithms, we can identify where the bends are, the columns and piers are. Not all of them are visible in all of the images, but a synthesis of all the images will give you more or less everything that you need. We identify other important details like the seat lengths of the in-span hinges. In California, some are shorter inadvertently and they are prone to collapse. So this seat length is an important parameter to extract. We compute the super elevation from the posted speed data on the bridge so we can get the bridge dynamics, the mass distribution in a more accurate way. We extract column images, convert them into edges. From those edges, we automatically extract column dimensions. And again, hundreds of images combined will get you a very fine accuracy, below centimeter accuracy from basic red, green, blue photographic images. Here's a resulting model against the actual picture. It looks good, but as engineers, we cannot just go by the looks. We have to test it. So we've tested it against the actual data. You're seeing the deck centerline elevation extracted from image-based models versus the actual as-built drawing data. Again, you can see we're very accurate. These are various column dimensions from as-built structural drawings versus image-based model. Again, we're very accurate. We compare the two models, the model we created from images versus the model we created from the structural drawings, and looked at their natural frequencies and mode shapes. And as you can see, we can model the mass and stiffness distribution of this bridge quite accurately just from images and basic information. What's nice about this workflow or this toolbox is that it can be automated to thousands of bridges. And the bottom line is how accurate is the fragility curve that I obtained from the as-built drawing model versus the image-based model. And as you can see, this fragility curve between the two options is quite accurate. So this means I can use this in regional scale assessment of what may happen to a network of bridges in a given region. We've done many different bridges, you name it, and these are all automatically generated models. And we've applied this technology to, say, the Port of Los Angeles, which is one of the largest ports in the United States, where all the goods coming from Asia are imported into the United States and get distributed. Of course, the port structure's safety, seismic safety is important, but it is also very, very important to understand how the bridges around the port are connecting the port to the inland. And if those bridges are damaged, you cannot get goods in and out of the port. So everyone will be impacted. Even people in the Midwest, many thousands of miles away, will be impacted by an earthquake here. So we took a region of interest and we initially modeled 100 bridges automatically here. Currently, our model extends to 1,000 bridges around the port, but we've simulated an earthquake that is probable in that area. This is the map of Southern California. My location right now is in this map somewhere nearby. I'm just basically like 20 miles away from this Port of Los Angeles. We've simulated, say, a 7.7 earthquake, and then we've looked at analysis models and then obtained damage probabilities or damages to these bridges that we've modeled. Then we have collaborated with colleagues who do traffic analysis to examine how this kind of earthquake would impact, and those damages would impact the traffic and economy in and out of the port. And then we created these damage loss curves. As these damages were repaired over a few months, then you're losing this much traffic volume and commerce volume. So we could communicate this to the government and tell them the true value of those bridges, which far exceeds their nominal value. If a bridge closes down around the Port of Los Angeles, the amount of money it loses in a day is millions of dollars. And in a few days, it will have been just losing a lot more money than its nominal value. So bridges are extremely important. So these types of analyses can illuminate that type of result. We've also created computer vision-based, machine learning-based tools for buildings. These are tools I directly led the development for Brails++ and Fortuna. Brails++ and Fortuna were developed specifically initially for hurricane hazards, but we've extended them also to earthquake hazards recently. So as long as you have images from the streets that you can obtain using basic cameras, we can create models of these structures quite easily using different types of algorithms. We've applied this technology recently to school buildings in, again, the city of Istanbul, which is home to many children and hence are very important. So we're now doing an analysis with the government of Turkey to assess the vulnerability of these school buildings in this pilot's region to be extended to other seismically vulnerable regions of the country. You can also, as I mentioned before, extract information from post-earthquake survey data, and we have done so with colleagues in Turkey who investigated approximately 2.1 million buildings in the country after the 2023 earthquakes in Turkey. And using those data, we have created these empirical fragility curves. By that, I mean we've collected data about different classes of buildings. They were all exposed to different seismic intensities. And then we created these graphs which tell us, given a seismic intensity, what is the probability of experiencing a certain level of damage? And these are very, very valuable ground truth curves, which we have recently published. And these kinds of fragility libraries can be created for different countries and different regions. So rapid post-event assessment is another element of hazards engineering. When an earthquake happens, you need to answer various questions. Do we need to stop operation and evacuate? When will it be safe to return? Where should we send the first responders? And then also, can we quickly assess the damage? And in that last question, there are several sub-questions, which is there damage in the system? Whatever that system is it a hospital, school building? That's detection. Where are the damage components? That's localization of damage. And those two questions are relatively easier than the last one, which is quantification. What is the loss of strength and stiffness? Can I determine these? If you can answer these three questions, then you've done an excellent job. They're not easy. The typical approach around the world right now is generally visual inspections. Visual inspections are subjective, labor intensive. They're not going to tell you especially the answers to that last question. If you have a tunnel lining that's cracked, then I ask you, like, what is the loss of strength? It's not easy just by visual inspection to answer that. If you have hidden structural members like pile, foundations, you need to dig them up to see what kind of damages they may have suffered. So that's one lingering, that's one option, but it's not a very fruitful option. It doesn't scale well to regions. Another option that scales well to regions that is now becoming very, very accurate, which we've applied again to Turkish earthquake data, is using unmanned aerial vehicle images and satellite images, especially microsatellites that give you very fine resolution images from the sky. And then by training a machine learning algorithm, within minutes, you can assess the damage in a large region in broad clusters. This is detection and localization of damage, but not necessarily quantification of damage. But you can do that, and this is feasible. Of course, if you send out vehicles with cameras, now you can get a much more detailed assessment, and we've done so. Another feasible option, which is much better than the labor-intensive visual inspections, is to have seismic instruments on buildings, especially important buildings like school buildings, etc. Seismic instruments have become cheaper. You can put them on buildings. You're seeing the study that we have done for the United States Department of Veteran Affairs. They have many hospitals. We have seismic instruments in those hospitals, and we've created software with which they can rapidly analyze the damage level in those hospitals after an event without sending anyone there by using the sensor data that was collected. And you can use the sensor data in different schema, combining them with fragilities to do regional assessment. And you can quickly tell what happens in a region, which buildings are safe, the blue ones, which buildings may have moderate damage like greens and oranges, and which buildings may have suffered severe damages like the red ones. And then you can focus on the red ones and you can do more detailed analysis if you have pre-prepared models for those detailed, for those assets like fuel storage tanks and hospitals and things like that. And we're doing these kinds of studies in the US with different partners. We've also created automated report generation capabilities so you can get these reports into your laptops in the field, et cetera, and distribute it to different partners. So some final thoughts in all of these things. Natural hazard risk assessment, as you've seen, is highly interdisciplinary. It's unlikely that one type of person can solve all these problems. You need computer vision, machine learning, social sciences, economy, structural engineers, et cetera. So if you want to address these problems, be ready to collaborate with colleagues. So that's one important aspect of natural hazard risk assessment. Another important aspect of natural risk assessment is that it bears many uncertainties. You cannot work with deterministic models. Your models will have to be probabilistic models. And in that, there are two types of probabilities. One is epistemic probabilities, which are the natural variabilities in the events that you're observing, like probability of having an earthquake. That's naturally an epistemic problem. But there are also aleatory uncertainties, which is you do not know exactly the model, the strength, the concrete strength, the rebar ratio, et cetera, of your buildings. And you don't have necessarily perfect predictive models of what damages will ensue. So those are modeling errors. While we can only accommodate the former type of uncertainty, the epistemic uncertainty, so we create probabilistic models of earthquakes exceeding a certain level, we can definitely focus on the aleatory modeling errors and reduce the modeling errors by doing better models, doing a little bit more research before the events, so we can control the aleatory uncertainties. And in that, my recommendation to everyone working in the field is to use physics-based models in general, and they will enable rational bracketing of the model errors. So because they're physics-based, they will not give you nonsensical results. They're eliminating those by automatically, inherently. Also prevents natural laws like Newton's laws and thermodynamics laws from being violated in your predictive models. And then presently available algorithms, whether they're physics-based or data-driven, and high-performance computing resources are currently at a level where we can do analyses of entire cities. And I've shown you these examples with relative ease. You just have to put some of the resources and the teams together, but it's possible to do all three types of pre, during, and post-recovery types of analyses in super detail that can be useful for planning and mitigation. So that concludes my presentation. And I'd like to acknowledge also our various sponsors that helped us develop all this work. Thank you very much.
Thanks a lot, Professor Taciroglu, for your wonderful presentations. Okay, I forgot to inform the presenters how they should manage their presentations. So it'll be appreciated if you can wrap up your talk within 25 minutes and allowing 5 minutes for the quick Q&A, even though we will reserve last 30 minutes for the Q&A to all 4 presentations. Okay. So is there any quick questions to the presentation by Professor Taciroglu? Okay, not, we'll move on to the next presentations. So our second speaker is Professor Ji Dang, a associate professor in Civil and Environmental Engineering Department, Samata University from JSC. So he is working on the bridge engineering and earthquake engineering, focusing on the use of AI, UAV, and other emerging digital technologies in structural dynamics, structural health monitoring, and bridge maintenance. So please welcome Professor Dang. Professor Dang, it's all yours.
Oh, okay. Now it's okay. Now
Okay, I
I'm
can hear you.
host. Yes. Thank you very much.
Very good.
Oh, I think I didn't share the correct display. Okay. Am I sharing the correct display? I guess so. Okay. Thank you very much for having me here. My name is Ji Dang from Saitama University. And today I would like to share some knowledge about the lessons we learned from, oh, maybe not this slide. Yes, from the past of or experienced in Japan. So we are very focused on the Myanmar's earthquake, and we know that realize that there are many damage happened in Myanmar earthquake. We are trying to do more survey, and we also realize there are some damage in Thailand also. And we hope we can have more chance to communicate with the colleague in Myanmar to explore more researchers. And this year is the 30 years anniversary of the 1995 Kobe earthquake, as many of you have been realized that, which earthquake brought great damage to bridge structures in Japan. And this is also the 45th years of JSC Earthquake Engineering Symposium which conducted in Kobe City. And so we also have the special seminar, special session for Myanmar's earthquake. A lot of information about Myanmar earthquake have been shared recently. And I visited Kobe City, and I see that if you can see some part of the old damaged port have been reserved here, and also some bridge piers being reinforced, and also some pier using base isolation under the pier, which is quite rare, I think, in all over the world. So a lot of lessons have learned in the past earthquakes. Also, after the 1995 Kobe earthquake, we also have unfortunate a lot of earthquakes after that. For example, the 2011 Toho earthquake, which also caused a lot of bearing damage for bridge structures. And unfortunately, so 2016 Kumamoto earthquake. And also a lot of bridge bearing have been damaged. And from that, we are starting to use UAV to take pictures of bridges, as you can see in the left-right corner, because some bridges quite difficult to access, and some angle are quite difficult to be seen from above the bridge or under the bridge. We need some camera on the air to get the information from the bridges. Also, I realized that just in the recent, there is a large earthquake happened in Philippines, in Cebu city, and there's many damage has been reported, and dozens of people have been reported lost their lives. I hope the people in the on-site are be safe, and hope the more and more information can be cleared about this large earthquake. So as we can see that the earthquake around Pacific area and the Asian area have been more and more active, not only in Myanmar, Bangkok, but Indonesia, Philippines, as much as in Japan. And after the earthquake, we need to do some inspection of bridge so that they can emergencyly make sure the bridge is safe and restart the transportation function of the bridges, which is quite a hard work to do, because we need sometimes we need some large scale machine or some specific tools to do the inspection, which makes a lot of rooms to use UAV, which is drones, to take more close look, especially for the situation in the bridge, which have damage. So last year, 2024, a large earthquake hit Japan in the Noto Peninsula area, which have caused a lot of damage of bridge and also as the human residential buildings. As you can see that some of the recorded quite a long period shaking, and also a lot of places were recorded acceleration on the ground level in the 1G, over 1G ground level earthquake. And from the response spectrum, you can see that sometimes recorded 4G or 5G response, which of course maybe some problem of the earthquake recording, something of the fix of the anchor may have some problem. But we see a lot of this kind of large earthquake, which is so much higher level of earthquake than the design specification. We conducted some on-site inspection on the bridge. and in the Noto Peninsula area. One of the bridge is called Twin Bridge Noto. This bridge is a quite large-scale bridge, but unfortunately there are two bridge abutments have experienced large damage. Also, we can see the pier area also experienced a quite large damage. However, as you have this kind of damage, it's quite difficult to let the elevation car or inspection car go above the bridge, so that we can now see what's happened under the girder of the bridge, especially the bearing area and the pier area. So it uses UAV to inspect this bridge and find the damage of the RC pier around here. And also use the UAV video, we reconstructed the 3D model of the bridge so that we can take a better view of which part and how is damaged of the bridge. From the video, you can see quite detailedly on the surface cracks, which is not caused by earthquake, I believe. They may caused by the extraction on the surface of concrete oiling, but we can see the quite clear information on the bridge. Also, we take quite a few times of UAV inspection on the bridge and take overall information on the bridge so that we can make a whole bridge structure model on this bridge. As you can see that the P3, Pier 3 also have a basement bending caused damage, and which is FRP reinforced bridge, and FRP was also being broken on the basement. Also other piers like P4 here, their bearing part have been experienced some damage, so that we can have an overall image of the whole bridge, including the sedimental part of the bridge and the end of the girder part. This is not very clear, but we can get the whole image of the bridge. Also, area called this is the area which is one of the most shaken area. And after the large earthquake, almost all the buildings, over 50% of the building, have been damaged on this small town. And also they experienced very large tsunami over 2 meters high, and a lot of buildings around the offshore area have been secondary damaged by the tsunami. So we use UAV to take a flight and regenerate this 3D model to capture the situation exactly after the earthquake. As you can see that many buildings have been damaged, and we can check building by building what has happened there, and we can also do a very fast evaluation of how many garbage need to be dealt with, which can help in fostering the recovery of the area. This is the only bridge have been found that have near to failure status. One part of the bridge have been collapsed, which is the penetration bridge have been found damaged, and other part of the bridge also been really damaged. This is the Ukai Bridge. So not only in the Noto earthquake, but other part of the earthquake happens quite oftenly recently. For example, the large earthquake happened in Russia and in July, and caused a great tsunami, which is make Japan very nervous about. So due to this kind of situation, that we find that we should do something using UAV and digital twins of this bridge structure, so that we can fasten the process of inspection and recovery of the bridge. As a law of Japan, that after some certain level of earthquake, all the highway, at least the preliminary lines, about 30% of the whole highway needs to be inspect immediately in 3 hours after the earthquake so that they can reopen the bridge. So people need to walk down under the bridge to check their safety of the bridge so that to give the evidence to reopen the lines. So due to this kind of difficulty of in short time and large amount of checking on the bridge, we propose to use UAV and digital twin to fasten this progress and make everything automatic and faster. So one of the research is using the UAV taking picture and AI to regenerate the 3D scene of the bridge under the girder, especially the pier part. So the general way to generate the 3D model I've been showing you until now is generated by the method called SFM, which is from picture to picture and to point cloud to point cloud generation. But this one is right corner picture is generated by AI. So you just give any angle of the system of the scene, then you can extract the 2D image generated by the AI. After analysis, all the analysis result from the pictures they took under the bridge. Also from this kind of 3D model scene, and we can also extract the point cloud of the pier, which quite high accuracy. And we tried many methods, including using smartphone plus SFM, UAV SFM, and smartphone nerve and UAV nerve, and using smartphone LiDAR to generating the 3D point cloud. You can see that each model have their accuracy and also have their difficulties. We are still wrapping up this kind of research. Also, we are trying to understand how to make 3D model easier to use. For example, we have a 3D model that we are trying to generate their automatic image so that we can get a 2D plan view of the whole picture, which is typical to be captured by one camera or one photo. But we can, using this kind of recaptured mosaic or also photo, to detect the damage on the bridge using AI after we getting this kind of high accuracy result. For example, for the pier, we have a 3D model pier that we can expose them to the full size of the pier and to detect damage one by one scene. So we call this a 2D AI damage detection. Right now is for deterioration of the bridge, but I think future we should use this for the earthquake damage of the bridge. Another recent research is using AI to detect piers local buckling. As you can see that in Japan, especially in 1995 Kobe earthquake, that the major damage of the pier is happened in the steel pier, which is local buckling. However, the information about earthquake damage in local buckling is quite rare. So in this research, we used a transformer model and generative AI to generate some damage photo to help AI to detect damage more accuracy. So we split this kind of photo as level 1. This is the experimental generated picture, level 2, and this is level 3 of a different local buckling failure degrees. And also we use AI to generate a data set. So this is level 2, and this is also level 2. You can see this generated AI have some mistakes sometimes. Actually, this is not possible in the real world. If this crack like this or they collapse, but somehow they generate some very shocking damaged pictures, which is also very interesting for us. And then finally, we test on the real data set that we have been observed, not very much on the Kobe earthquake in 1995. So this is a training result, and AI tell us that this is predict level 3, level 3, and level 3. So actually, this may be a bit more between level 2 and level 3, but these two are actually quite a large damage. So The next step is to diagnose the structural damage for people using smartphone application, because right now, especially for the developing country, that after large earthquake, we need experts to go to the site to do a proper detection of the building. Until then, the building are not being recognized as safety to be living. People will be very nervous about this kind of buildings. So that we propose to make a smartphone application using AI that can helping everyone to check their house is safety or not. So basically, we will have firstly have a outdoor picture to tell them is safety or not. So if it is safety from the outside picture, then we let people to go into the door to take an indoor picture. If it's not safety, then people are told do not enter the house. And there's a lot of international standard about how to tell the damage of the building. I just got it very fast. And finally, they will tell you green, yellow, and red by the considering both outside and indoor and outdoor images. So this is a result detection outdoor pictures we use YOLO model. For example, this one is obviously not safe to entry, but this one are looked safe to entry. So the other pictures we collected from recent earthquakes. And then we use some standard to tell the different structure members of the image we take in indoor, and use some standard to check the level of structure damage, like level 1, level A, type 1, type A, type B, type 3, or this is just a infill wall, it's not structural wall. So if you see a steel bar, we think this is a structure member. If you see no steel bar, even this larger, we think it's the infill wall. Especially it's working for the RC structures. So instead of the expert, we can use this application to help people to check their building with 3 levels of their building. After detection of each level, we also give them a weighted damage index to help them to get the result. So this is a demonstration how the smartphone application works. Users take damage pictures and to tell, let the AI to detect. So the AI tell you, okay, this is now safe to go, right? And you can select other pictures to let AI detect, then also same result. And if you have indoor pictures, AI can also give you some evaluation of indoor pictures, something like this. Okay, but sometimes the 3-color classification is not enough. We may need more detailed analysis about what is happening on the structure. So we use image captioning and language, natural language process model. For example, we give a image photo to AI, so AI can tell us what's happened on the pictures. But obviously, it's not enough for us because sometimes we need other information and higher accuracy about what's happening there. So we use attention to the transformer models. So that they can give us basically some caption about what's happened there. And we also connect some non-visual information, for example, the PGA, PDV of the area, and give them to large language models, such like ChatGPT, to give them some more useful detection result. For example, this is a prompt engineering format. We give them a case damage, the building age, image captured, and give them to the ChatGPT, then ChatGPT can give us some expressions of what is happening there and what we should do. And so here is ChatGPT's answer. And they not only give you the answer of what is the level of the structure, but also give you some result that you need to immediately evacuate from this building. So there's also not only the threat is not only caused by earthquake, the city hazard happens due to other reasons. For example, collapse of understructure pipelines, and we also find that the case will happen in Japan, but this one is happening in Thailand just recently. Large scale collapse of the road due to some reason of the collapse of understructures. And also challenges come from the heavy rain recently. I believe this one is from Korea, and this one from Japan. A lot of bridge was scored up and even collapsed during the large heavy water flood. And for example, this one is a bridge scored by the flood and then tilted after the flood. And this kind of situation happens quite oftenly. For example, one of case we surveyed in Kenya is that their abutment have been scored very heavily, and after that they repaired it with some reinforcement. This kind of case happened quite oftenly, not in Kenya, but I think also in other countries. So that before and after the flood, we take images of the bridge using UAV and make 3D models, so we can compare from above to see what is changed on there. Also, we can use DM model, which is elevation model of each grade of the 3D model on the mapping compared to the before the flood and after the flood. So you can see what is happening here. For example, here we can see this area are the bridge surface, so nothing happened. The right part means the elevated part, and the blue part shows the rehappening of the scoring, which is threatening the new repaired abutment. So this is implying us that to reinforce the bridge even further. This is another bridge happened in last year in Kenya, named Seismic Bridge, which had been constructed in 1997 with the help of the Japanese government. And as we surveyed in the 2023, and the bank is quite wily. There are other trees around the abutment, but after the flood in 2024, the erosion going on quite fast, that it's already threatened the basement of the abutment. If we didn't do anything furtherly, it will happen. Same with Seismic Bridge, what have been shown before. And heavily, we have the Google satellite result just before the flood. So we use this one and compare to our UAV mapped above photo, mapping the photo there. And we also measured the area of lost before and after the disaster, so that we can calculate accurately the erosion areas. So this is Seismic Bridge we have been shown before. So let me pass this one. And I think that's all from my side. Thank you very much for listening. So I think maybe a little bit time for questioning and answer.
Very good. Thanks a lot, Professor Tang, for your nice presentations. Okay, yeah, we have a quick questions from the audience. It's Kelvin. So could you turn on your microphone and say the questions by yourself? Or
I see the question. I see the question. So Kevin
Okay.
is asking question one from the UAV and smartphone comparison of 3D model. Please share the key difference in terms of point cloud accuracy. Okay, thank you very much. I will share the desktop again, and I will explain a little bit more detail on that slide, which I didn't have time to explain in detailing. So this is a smartphone plus SFM. So we just take smartphone under the peer and then reconstruct them, so that you can see that there are a lot of red and empty area which didn't be reconstructed to the whole structure. But if we use smartphone LiDAR, we can reconstruct it all the area with very few area of red area and almost no empty area on the peer. So in the basement part of the peer, smartphone LiDAR have showing great accuracy. And we also lost some area of the surface in the base of the peer due to the smartphone or UAV-based nerve method. But we get quite a stable result using the UAV SFM method, which is quite traditional method and and which also economic method, but get quite good results. So 1 and 2, 3, 4 shows the order of the accuracy of the result as we evaluate as much as now. Hope I answered your question. So your second question is, you mentioned the train AI using a vision transformer to detect local buckling in still peers. Could you explain why transformer chose over CNN, and what data set challenges exist with earthquake spectrum modeling? Thank you very much. Let me share the desktop again and go to the part of the this research. So we instead we use CNN to do the classification. This time we use a transformer model to do the simulation. So one part of the reason is very simple, that transformer model have a originally a little bit higher accuracy than the CNN model, not very clearly, but a little bit higher accuracy than CNN models. And the other reason is that we have very few data of damage, especially local buckling data. We can only get them data from our experiments, laboratory experiments, or from generated AI, and using the real world damage data only for test. So that in this kind of case, transfer model have so much more higher ability to capture the feature of damage of the structure than the traditional CNN model, as much as we observe. But thank you for your question, and we think we should try to compare two methods in accuracy level. Thank you very much for the question.
Okay, thanks a lot. Professor Tang, actually, we have additional questions to your presentation from Keither Mint. But if you can make the quick answer to that, you can go ahead. But if you can do right away, we can reserve that Q&A at the later part of the session.
I can just make a very quick response to the Mint. I think his question is about the complaint of the check of the ChatGPT. I'm so much agree with you that ChatGPT sometimes give very good result, but sometimes gives very not good result, because I check my students' report and they use ChatGPT sometimes. So sometimes they didn't give us very good result. So we should be very careful of using ChatGPT. Thank you very much.
Thanks a lot, Professor Tang, for your nice presentation and Q&A also. So let me invite the next speakers. So next speaker is the Professor Iswandi Imran. He's a professor in the Department of Civil and Environmental Engineering, Bandung Institute of Technology from Indonesia, who has been recommended by Haki. And okay, Professor Imran is all yours.
All right, thank you. You can hear my sound clear?
Yes,
Okay,
clearly.
thank you. Yeah, thank you, Chairman. Good afternoon to all colleagues in Asia, and also good early morning to all colleagues in other part of the world, especially in the US. The title of my presentation is Lesson Learned from Several Recent Damaging Earthquakes in Indonesia. I have an affiliation with the Indonesian Society of Civil and Structural Engineers, HAKI, also with ITB, and also the Indonesian National Center for Earthquake Study. Yeah, these are the outline of my presentation. Yeah, I will start with introduction and then go to the example of damage due to recent earthquake in Indonesia, the causes of the seismic induced damage, and follow with the strategies to improve the resiliency of infrastructures. And at the end, close with the closure. Yeah, these are the shows the records of earthquake in Indonesia for the past 100 years. Yeah, circle dots indicate the earthquake epicenter. The larger the circle, the larger the magnitude, and the red and orange colors indicate shallow depth up to 50 kilometer. You can see that we have so many earthquake sources throughout Indonesia, especially in the western part of Sumatra. Yeah, this is Sumatra actually. Yeah, that's the Sumatra. The southern part of Java, eastern part of Indonesia, Sulawesi, Maluku, and also Papua. I cannot move this. Okay. Yeah, in the following slide, we'll show you various structural and also non-structural damage due to the recent earthquake in Indonesia. This is from the Palu earthquake in 2018. Yeah, I think it's quite well known. Yeah, because during the earthquake, there's also some, disasters. Yeah, due to the liquefaction. Yeah, the magnitude is 7.5. Palu is the provincial capital of Central Sulawesi. Yeah, various kind of damage found in building structures there, such as sub-story. Yeah, in this building. Yeah, due to the weak columns and strong beams, some joint failures. Yeah, that caused the collapse of the buildings. Yeah, and we have also a bridge collapse. Yeah, due to that earthquake. Yeah, the bridge is used to be the landmark of the Palu city. The upper structures collapse is due to the failure of the corroded anchors connecting the upper structures with the substructures due to the local tsunami on that location. So actually this bridge is located in the front seawater of Palu City. This is from the Lombok earthquake in 2018 with the magnitude of 7.0. Lombok is in West Nusa Tenggara province. Various kind of damage are found in building structures there, such as pounding, yeah, like this one, due to the inadequate gaps between buildings, and also column failure, yeah, due to the heavy floors above, yeah, and also short column phenomena because of the presence of walls in the surrounding of the columns. Yeah, this is from Mamuju earthquake in 2021 with a magnitude of 6.2. Mamuju is the provincial capital city of West Sulawesi. Yeah, this is the governor's office building. Yeah, before the earthquake. Yeah, and this is after the earthquake. It experienced partial collapse, especially in the front side of the building, because of the heavy, strong irregularity. Yeah, of the building. Yeah, you can see here some inclined columns and also some kind of irregularity in the stiffness distribution. Yeah, in this part of the building. Yeah, this is another example. This is one of the precast concrete buildings in Mamuju. Yeah, the damage is due to the failure of the connection, yeah, of the precast system. Yeah, you can see there a lot of failure in the connection because of the probably, yeah, the connection is not able to sustain large deformation demand, yeah, from the earthquake. This is from the Pasaman earthquake in 2022, yeah, with a magnitude of 6.1. Yeah, Pasaman is one of the regency in West Sumatra. Most of the buildings in Pasaman is one-story residential houses categorized as non-engineered building. Yeah, this is the typical damage found in the non-engineered buildings in Pasaman. Many people have like heavy canopy, yeah, supported by architectural columns, inadequate, incomplete tie element, yeah, in masonry wall. So the masonry wall is not confined; it's kind of unreinforced, unconfined wall. Yeah, inadequate maintenance. Yeah, you can see the change in colors. Yeah, because of not enough maintenance. Yeah, during the operation of the building. Yeah, unsound roof structures. Yeah, you can see. Yeah, the support is not that adequate. Yeah, not enough attachment and incomplete element as well. Yeah, in the structures. Yeah, this is another example. Yeah, the collapse of the masonry wall. Yeah, because you can see there is no tie element at all. Yeah, in this wall. The same. Yeah, also in this wall. Yeah, and also the maintenance. Yeah, also the problems. Yeah, because you can see the change in colors. Yeah, also the wood. Yeah, structures already becoming deteriorated. Yeah, because of the aging. This is another example, yeah, from Cianjur earthquake in 2022, yeah, with a magnitude of 5.6, yeah. Cianjur is one of the regency in West Java Island in Indonesia. Non-engineered buildings, yeah, dominate the type of construction in that area. Yeah, this is the typical damage for residential house there. The same like in other places, yeah, like the one that I just saw you before. Yeah, the unconfined machinery, unreinforced machinery, yeah, not enough maintenance, yeah, all sort of problems, yeah, similar, yeah, we found in this area. Yeah, this is a typical example of seismic induced damage, yeah, on non-structural elements, yeah, of the building, yeah. The ceiling on this big meeting room, yeah, fell down, yeah, because of the buckling of this frame. Yeah, you can see the frame is so small, the size. Yeah, this is sometimes we call it the light steel frame, yeah, but not enough stiffness, yeah, on the side, yeah. Even though the span is quite large, yeah. So what happened, we don't have enough ties on this or strut element on this side, then the opposite wall tend to move, yeah, in out of patient, yeah. So that's of course cause the ceiling fall down, yeah, and then also the buckling of this light steel frame, yeah. Yeah, this is a typical example of damage on stair structures. Yeah, we have always so many problems, yeah, in the stairs after the earthquake. Yeah, because in most practice in Indonesia, the stair is assumed to be separated, yeah, from the structures. So in the model, they don't include the stair stiffness. Yeah, but then in the construction, they make it as a monolithic one. Yeah, so they connect the stair at the top and also at the bottom. So in the event of the earthquake, it's becoming like a strutting element, yeah, in the building. So it will attract a lot of inertia forces, yeah, to that area, causing a lot of damage, yeah, including to the stair itself and also to the surrounding, yeah, like what it is shown here. Yeah, yeah, the same. This is also the same case, yeah. In the model, it is not connected, but in reality, in the construction, it is connected. Yeah. So it's becoming kind of a strutting effect, yeah, when the upper structure move relative to the lower structures, yeah. Yeah, there are the causes of buildings. These are the causes of the building, building damage or collapse due to the earthquake in Indonesia. Yeah, one is the inconsistent design, yeah, especially related to detailing requirement. Also, the improper seismic design consideration of non-structural component. Yeah, in many cases, their design are lacking, yeah, in seismic consideration. Also, higher seismic hazard in several area, yeah, because sometimes we don't have enough data, yeah, for developing the seismic hazard map. So until lately, then we know that in that area, yeah, there is a newly identified faults that of course will increase the level of seismic hazard in that area. Yeah. Inconsistent construction, yeah, that's also the cause, especially related to material and construction quality and consistency with the design, like the one that I just showed you, the example of the stair design, where in the design, yeah, they assume that it is separated, but in reality it is connected. Inadequate maintenance, yeah, I show you many examples of that, yeah, material deterioration, aging, and etc. And sometimes seismic design is also too high, yeah, due to many factors, yeah, such as structural irregularity, unisolated non-structural component, yeah, such as stair, unnecessary excessive mass, inadequate gap, yeah, etc. Yeah, most of this actually, I think, yeah, in Indonesia, yeah, due to a lack of enforcement, yeah, in the design and construction and also during the operation of the building. Yeah, based on the facts that many structures, infrastructures in various places in Indonesia experience significant damage every time big earthquake occur, our government, yeah, through the Ministry of Public Work, yeah, develop risk mitigation strategies to improve the resiliency of structures and infrastructure in Indonesia. The strategies are listed here, and we will discuss them one by one. Okay, the first one is conduct reconnaissance studies, yeah, to obtain lesson learned from every seismic event. Yeah, so actually we don't do this before, but since the last 10 years, yeah, we do it consistently. Yeah, so every time we have the earthquake, yeah, we have teams, yeah, that do the reconnaissance studies. Yeah, I'm sorry. Is the sounds in the background sound disturbing or not? Hello? Hello?
The sound is okay.
Yeah,
It's
sounds
okay, yeah?
okay.
Because there is a background sound from the mouse, yeah? Okay. Hold on. Yeah, these are the example of the reports, yeah, for every different earthquake, yeah, Cianjur, Lombok, Palu, yeah, Tasik, yeah. The report discuss many aspects from upstream to downstream, yeah. This includes the geological aspect, geoseismological, geotechnical, structural aspect, and etc. Yeah, so many aspects are discussed, and then after the completed the writing up, it is published, yeah, and then open to the public, yeah, to look into the report. Yeah. So we hope that this report we can get some lesson learned, yeah. Yeah, this is, for example, the finding, yeah, reported in that report, yeah, from structural aspect, the improper seismic detailing, yeah, found in the collapsed building, yeah, like the one shown on the left-hand side figures, inadequate confining reinforcement and wrongly placed splice connection, yeah. Strong beam, weak column, yeah, on this side you can see, yeah, the size of the beam is larger than the column, so that's why it experienced some problem. In addition, there are not enough confining reinforcement, yeah, in the joint, yeah, and this is also a problem that sometimes we found on field, yeah, incomplete hoops, yeah, you can see the hoops there stop in that location, and then they do some welding to the longitudinal rebars, yeah, which is not I mean, like actually not permitted, yeah, to do so, yeah. Yeah, this is another example, yeah, the same problem with the seismic detailing, yeah, the use of 90-degree hook, yeah. We're supposed to use 135-degree hooks, yeah. If you use the 90-degree hook, of course, under large deformation demand, yeah, this hook will easily loosen up, yeah, like what it is shown here in this picture, yeah. And then confining rebars are sometimes not adequate, yeah. This, you see the core of the column, yeah, experience some crushing, yeah. It's not supposed to be like that if you have good confinement in the columns. Okay, the second is to do continuous updating, yeah, of seismic hazard map. Yeah, this slide shows the evolution of the seismic hazard map of Indonesia. Yeah, The current one is issued in 2017. So the difference between the old one and the new one is the older one used the 200 return period earthquake. And since the 2002, we use the 500 return period. And then from 2010 up to now, yeah, we are using 2500 return period earthquake, yeah, for the seismic hazard map. Right now, the Indonesian Center for Earthquake Studies is working on updating the map. It is going to be the 2025 seismic hazard map of Indonesia. Yeah. And of course, yeah, the update is due to the availability of data from recent earthquake and also from geological and geodetic research. Yeah, that of course, yeah, we got more data from that activity, and it is then included, yeah, in the development of the seismic hazard map. So this is just to show you, yeah, in the seismic hazard map 2010, we only have 81 active fault line, yeah, and then increasing to 295 in seismic hazard map 2017 that we have now. And then in 2025, yeah, the one that is still under finalization, yeah, the total number is 402 active fault lines, yeah. And of course, yeah, due to this, there will be some increase in some area in Indonesia regarding the level of hazard to be considered, yeah, in the design. Okay, the next one is regular updating, yeah, relevant code and standard, yeah. We try to do it consistently every 5 years at least, yeah. For seismic design, for example, we have two big codes, yeah. The first one is for defining the seismic load demand. Yeah, we call it the SNI 1726, yeah, 2019. That's the last one. And also the code for detailing, yeah. Each structures, each type of construction material like steel, we have SNI 7860. And for concrete, we have the SNI 2847. Yeah. Yeah, that's the example of the cover page of the code. Yeah, the seismic loading code. Yeah, this part. Yeah, is now being updated. Yeah, as the new Indonesian seismic hazard map of 2025 will be issued soon. Yeah, so of course there will be some changing. Yeah, in the map itself and also probably in some of the provision related to the design of buildings. Yeah. Yeah, that's the code for the seismic detailing, yeah, for steel and also for the reinforced concrete, yeah, the same, yeah. This codes now is being updated, yeah, and for the concrete code, yeah, we usually refer to the ACI 318, yeah, and for the steel structures codes, yeah, we refer to a lot to AIC 360 and also AIC 341, yeah, for the seismic detailing, yeah, like this one, yeah. All these codes are now being updated, yeah, to of course adjust with the current state of the art that already developed abroad, yeah. Now, this is the code for the bridge design. Yeah, this is also being updated this year because we're gonna have a new seismic hazard map of Indonesia. Yeah, 2025. Yeah, of course. Then because of that, we have also to adjust to update. Yeah, the SNI. Yeah, for bridge design. Yeah. Our government just issued the new SNI code, yeah, for seismic design of tunnel and underground structures this year. Yeah, this is of course because lately, yeah, we have so many new tunnel, yeah, being constructed, yeah, for subway, for highway, yeah, for trains, yeah, and then up till last year, we don't have any codes, yeah, that can be used, yeah, to guide us to design the tunnel, especially under earthquake. Yeah, so that's why our governments initiate the development of this new code, yeah, to help the engineers to design a tunnel, especially under seismic load. Yeah. We also have a new SNI code, yeah, for seismic evaluation and retrofit, yeah, of existing building. Yeah, the purpose of this SNI is to mitigate risk of collapse of existing buildings due to earthquake. Yeah, which is usually designed based on older code that has, of course, sometimes lower seismic hazard. And it is also related to the requirement for function worthiness certificate of building structures in Indonesia. So this is the code. We have a cooperation with AACE to adopt AACE 41 as the SNI for seismic evaluation and rehabilitation. So now the SNI already issued, has a number 92723. So we hope that this can be used by our engineers when they do the seismic evaluation and also retrofit of existing building, especially in the area that already known has increase in seismic hazard. Now, as most damage are usually found in non-engineered buildings under earthquake, our government also makes a lot of effort to develop guideline to help people in constructing earthquake-resistant houses. These are the example. A lot of guideline already being developed, and some of the guideline is actually available in the website, so you can also get it. Otherwise, I can also send it to you if you need it. But problem is it is written in Indonesia. The same. This is, for example, the guideline for non-engineered building. It is written in Indonesia, but a lot of figures. So sometimes we don't, even though we don't understand the language, because the figures is there, you can also follow. The procedures, without any problem. The next one is applying state-of-the-art technology to reduce seismic demand, including to existing structures. Now, Indonesia lately already produced, we call it anti-seismic device, such as lead rubber bearings, LRB, Indonesian product, because we have a lot of rubbers, so they use our natural resources there to develop the lead rubber bearing. Now many elevated projects and hospital use this device to reduce the seismic forces and improve the performance of the structures. So already being applied in many elevated structures. Like for example, this one, the LRT, the highway in Jakarta. And of course, we hope by implementing this approach, we can reduce quite significant the seismic forces to the structures and also improve the performance of the structures. The next one is implementation of government regulation to control building permits. So hold on. Regulation has been established, especially applied at the design stage in order to control the quality and SNI conformity of the design product. And these are, for example, achieved by the establishment of Building Advisory Committee, TPA we call it, in all cities in Indonesia and also regency in Indonesia. So this is actually controlled and monitored by Building Safety Committee in Department or Ministry of Public Works. Already, I think, going on in the last 5 years, this process. Bridge Safety Committee, Bridge Safety Unit is also formed in the ministry. The role of the committee are also expected during the construction, maintenance of bridges, especially the non-standard one. So this is actually the diagram, for Bridge Safety Committee and also Bridge Safety Units, that has some members from the university, being the expert panel that will evaluate the design, the construction, and also the result of the monitoring of especially the special bridges in Indonesia. Okay, the next one is develop risk map, yeah, for all cities and regency, especially those located in medium to high seismic zone. Yeah. Yeah, this is developed by making several scenarios of earthquake. The purpose is to identify the vulnerability and also the earthquake risk in the area. Yeah, this is the example of development of the risk map in residential area in Jakarta, the capital city of Indonesia. Yeah, we can identify from this the area with high building vulnerability. Yeah, you can see the red color here is high, yeah, vulnerability. Yeah, the yellow one is low vulnerability, yeah, and everything, and etc. Yeah, this is the risk map, yeah, for residential area in Jakarta. The same, yeah. Based on this map, we can identify the high risk zone, yeah, from this map, yeah. Yeah, the last one is to develop various retrofit strategies, yeah, for existing building, including for housing, yeah. Yeah, FRP jacketing, fiber reinforced polymer, yeah, right now is I think one of the popular approach, yeah, to be used for seismic retrofitting of existing building. So many existing building now is being retrofitted, yeah, using the FRP, and we have already had the SNI code, yeah, to support that. We adopt one of the ACI document, ACI 440, yeah, as the reference for this code, yeah, and already being used in many area of Indonesia. In addition, yeah, our Ministry of Public Work also developed a guideline for retrofitting unreinforced, unconfined masonry buildings, because this is always the problem in Indonesia. Every time earthquake occur, a lot of damage occur in the house or non-engineered buildings, yeah, and most of them is due to the inadequate tie element or the unreinforced masonry being used, yeah. So that's why it's easily damaged by the shaking of the earthquake. So the government issued this guideline together with JICA. JICA is from Japan, yeah, Japan Foundation, yeah, with the Ministry of Public Work, yeah, where if you look at the content of this guideline, yeah, it gives you step-by-step procedure, yeah, to do the retrofitting or strengthening of the masonry wall, especially the one without reinforcement, yeah. So you have, for example, to open the cement plaster, yeah, at the surface, yeah. After that, you put some wire mesh, yeah, and then you also put some nails, yeah, in order to put the wire mesh on place, yeah, and then again you close with some sort of cement plaster again at the end. This actually, the document is open to public, yeah. You can get it through website, or if you like, I can also send it to you, yeah, if you need it. As a closer, yeah, the design and construction of building structures resilient to potential natural disasters should be carried out consistently and properly, yeah. So between the design, the construction, yeah, you have to do it consistently. Periodic updating of the relevant loading and building codes and guideline is a must to improve the resilience of the design product. Yeah, this update, of course, must be followed up with the extensive dissemination throughout Indonesia. Yeah, this is an example of Indonesia. The role of civil engineering associations such as HAKI, yeah, the one that I mean, I'm the leader right now, is very much expected in this case. Yeah, in short, the contribution from all stakeholders is required to improve the resilience of built structures and infrastructures. Thank you.
Okay, thanks a lot, Professor Imran. I know that you have to leave soon. I mean, at 3 p.m. in Myanmar time. So are you available for taking a quick questions from the audience?
Okay, sure.
Okay, yes, please. Here comes the questions from Kelvin.
Hold on, I open the chat panel. Many collapses were triggered by heavy and anchor non-structural component like masonry partition and parapet. You also mentioned the guide for non-engineered buildings. How do Indonesian codes and practice deal with non-structural seismic design, which is often overlooked compared to structural elements? Yeah, actually in our recent code, of the SNI 1726 2019, where we also partly refer to the ACE 7, there is one section that discuss a lot about the non-structural components. The problem is this section is sometimes overlooked by the engineers, probably because we don't have enough like socialization to the people regarding this particular section. But the section is there, so if you follow that consistently, then of course you can get the sound non-structural components. For example, in that section it is mentioned about the how you have to treat the stair. You of course you have two choices there. You can separate it, so or you can make it as one. If you separate it, you have to be consistent in the analysis. You don't put the stair in the model, so you just put the mesh of the stair, but no steepness. And then in the reality, in the construction, you should do the same. Probably you tie in one in the upper side, and then you make it loosen in the bottom side. So in the event of the earthquake, then it will not acting as the structuring element. Or you can make it one, as a part of the structural element. But then if you do so, there is a requirement, for example, in the code, that you have to increase the effect of the seismic load on the stair in order to keep the stair to be elastic in the event of the earthquake. So you have to multiply the internal forces with the we call it the omega factor, upper strength factor. So that's how we do it. And then question number 2, you emphasize the importance of reconnaissance studies after earthquake. Beyond damage surface, what advanced technical data collection method have you applied in Indonesia to ensure that recognize directly informed seismic hazard model and code update? Well, the reconnaissance studies actually done by the center, by the Indonesian Center of Earthquake Studies, and also the same people, also work on the development of the seismic hazard map, because this group is comprises of all the experts, related to the earthquake, from the downstream, from the upstream to the downstream. The geological science, the geological, geology, the geoseismology, the geotechnical, the structures, and then also people from the we call it the what they call it. I forgot the name. But we are group people with different background, and then of course, every time the earthquake happen, we gather together, we do some reconnaissance study, and we take lesson learned out of it. And then some of the data, as for example, for the geology for the earthquake sources, for example, then of course it will be used by the group of people from the geological science to consider whether it is important to include it in the next seismic hazard map, and something like that. So we have already like hazard models and hazard programs, in the group, that can be updated consistently every time we have more data from the recent earthquake, something like that.
Okay, yeah, thanks a lot, Professor Imran. So I think we need to let you go now, right? You
All
need
right.
to catch up your trains.
Yes, high speed train. Sorry, I missed the time. I thought it is Indonesian time, starting from 1 o'clock, and when I entered the website, I mean the Zoom, it's mentioned that it start at 1:30. Sorry. Okay. Thank you.
Hello, can everyone hear me? Hello. I think that thumbs up is saying that you can hear me, and hopefully you can see my screen. Just let me try to, I've unfortunately got the screens the wrong way around here. So I'm just going to try to, there we go. Hopefully that is better. Can I get a thumbs up that you can see a full screen of my slide? Thank you. Well, good afternoon in Myanmar, and thank you for the invitation to share some experiences from recent earthquakes. I'm David Wood from Beca in Wellington, which is a very high seismic zone on a world scale. We have major fault lines passing through Wellington and a significant subduction zone just off the coast. Beca is a consulting engineering firm. We work in New Zealand, the Pacific, and Southeast Asia. We have an office in Yangon, and I'd like to acknowledge my colleague Myo Tunt, who's section manager for structural engineering there in Yangon. He was kind enough to make some suggestions on what might be interesting for you. First, I'll give some context on 3 recent earthquakes that I've observed directly after the shaking, within a few days of the shaking in person. Then some damage specifics from those earthquakes, and I want to focus on the benefits of better detailing, what we can do to detail our new structures better, and also to retrofit existing damaged structures or undamaged structures which have significant weaknesses. Then a little bit on a structural system layout illustration from the Christchurch earthquake to illustrate some key points that come up time and time again as we look at earthquake damage in different parts of the world. And then a very quick look at some low damage technology being used in New Zealand today. So I've attended 3 significant earthquakes just after the shaking to assist firstly in Christchurch in 2011 with USAR, Urban Search and Rescue, that I was part of. Then in Port Vila last Christmas, with New Zealand's Ministry of Foreign Affairs and USAR. And then the Mandalay earthquake, I attended Bangkok to look at the performance of some of the tall buildings that we've designed and a number of others. This slide is intended to show that there's quite a bit of variation in earthquakes. As we know, Christchurch, for instance, was a direct hit, only 10 seconds of strong shaking, and yet because of very high vertical acceleration of up to 2G and a basin effect of soft soils under the city surrounded by firmer ground, there was amplification of the shaking as well. And so even though it was only 10 seconds of strong shaking, very short, because it was a direct hit and had that amplification and that high vertical acceleration, some of the damage and loss of life was fairly extreme. Port Vila, that was really saved by the very short duration of shaking, and for the most part, very good ground, mostly close to rock, coral, limestone. And then the Mandalay earthquake, now that's different to the previous 2 because 80 seconds of strong shaking, that's a lot of strong shaking, and a huge displacement. I've seen a video of the ground displacement. very shallow, very close to Mandalay, and therefore a lot of damage there. And in Bangkok, because of the size of that shaking and the forward directivity from north to south towards Bangkok, and soft soil and basin amplification in Bangkok, tall buildings experienced the frequencies that got them moving. So not so much a direct earthquake pulse effect as excitation that got the long period buildings moving. So all of those earthquakes caused at least one significant collapse and sadly loss of life. In Christchurch, this is the CTV building where 114 people's lives were lost. And that was a total collapse apart from the core wall at one end. The result of the Christchurch earthquake in New Zealand is a new focus on good layout and detailing, a refocusing for buildings which are designed today and for buildings which are strengthened. And then low damage design because of the outcome cost, something like $50 billion worth of damage and effect on New Zealand's economy. And as a small economy, we can ill afford that. So there's been quite a bit of thought about significant commercial buildings and public buildings having low damage design. I'll move on quickly because got a few slides to get through here. In Port Vila, sadly, this was the collapse of a two-story commercial building, retail building, with loss of 14 lives. Interesting here that there's a building right next door that really hasn't been affected, and so that shows how specific building layouts can influence the effect, even one building next to another. The result there is a proposed change in seismic hazard levels. Detailing, that's a big question mark. And there's resistance to both hazard level increase and detailing improvements because of the cost. Here's a spectrum showing in the yellow here the existing seismic hazard in Vanuatu. And in the brown, that was the best estimate of USGS that USGS could give us on the spectral responses. Unfortunately, the one instrument that was close to Port Vila, the city, didn't have sufficient amplitude to record the earthquake, so it went off the scale very quickly, and that quite often happens around the world. And the proposed new level is about the green line here, green to the pink line, and seismic hazard assessments in the area suggest that it could be as high as here. So we're talking about a 3 to 4 times increase in the seismic hazard is likely to happen, and it could be as high as 6 if they were to follow, if the authorities were to follow seismic hazard estimates now, which have improved over time. So that just shows what they're facing. Here's another picture of a building collapse in Port Vila. This was the embassy building of New Zealand, United States, France, and the United Kingdom. And you can see there this colour line shows quite clearly that this side of the building has sat down. It appears that it sat down because this was an attempt to put a seismic joint in the building, and it was really put in without probably sufficient thought about how the two sides would respond together. So it would appear that this right-hand side, this is a conglomerate photo, so it's a bit messy, would appear that right-hand side's thumped the left-hand side down, and in the longitudinal direction, all of that column structure, which is leaning a little bit on this side, has been insufficient. in Bangkok, which was the other place I attended. There's a lot of tall buildings, and so many of them 60-story buildings, 50-story buildings, 70. Were excited by the distant earthquakes to their fundamental frequency. And so they underwent some shaking. Sadly, the State Audit Office building that was under construction and up to its 30 stories height, but not fitted out, collapsed with loss of life. And that's contrasted with Mahanakhon Tower, a 70-story building, which underwent 0.6% drift. So we'd expect at that level of drift that you would probably not get too much cracking. And so it was with this building, which is really, although it looks quite complicated, is a very large continuous core with some outrigger, couple of outrigger levels, and a very stiff, that 7-second period for a 78-story building shows us that that's a very stiff system. Got a little video here that's interesting to see. Let's see if it'll play. Just shows, if you can look at the building alongside, how that's drifting. And you can see a little bit of higher mode effect at the top. Critical locations in these tall buildings can exist above the base, and this shows first, second and third mode behavior. That means you can be looking at critical locations at the base, half height, maybe 1/3, maybe 2/3. It's not necessarily all that easy to predict because of the vagaries of earthquake shaking, particularly from a distance. This is an example in a 38-story tower I looked at. The stairs are often a really good giveaway of building movement. So this is precast stair, and it's got a seating, and it's cracked. You can see there's been movement here, but the stair is still seated. Here's some more. So this is at level 14, so part way up the building, 1/3 to maybe 40% of the height, showing some second, third mode, probably third mode effect. The stair here appears to be seated on some unreinforced block wall, which is concerning. But the movement hasn't been enough to unseat the stair. But that just illustrates that higher mode effect, and the tearing here through the landing initiated by those precast risers. This is spectral information that came through quickly from a university in Bangkok, and shows this blue and grey line is the relatively low level shaking experienced at a distance from the Seunghak earthquake, in distinct contrast to the closer, much closer, almost direct hit experience in Mandalay. And these are the yellow and green curves of the recent code design basis earthquakes, so 500-year return period earthquakes, and they're plotted at 5% damping, which is standard in international codes. This orange curve here shows that at around 6 seconds, tall buildings will get a quite an increase in seismic acceleration, because research is starting to tell us that tall buildings will probably only really have 1% damping, not 5%. So that's plotted at 1%, and shows that you can be getting up to 10% G experienced in Bangkok from that distant earthquake. Now that suggests that an increase in the minimum base shear of up to 3% G rather than the current 1% G is probably required, based on a normal ductility factor, R factor, from the American code approach of about 4. And some thoughts on what Thai seismic code could do. Higher structural system stiffness would be more dependable, result in less damage. This increase in minimum base shear, better detailing. I'll compare later, wall detailing that we've done with some other common practices in tall buildings, and the effect that can have. Building effects really are lower drifts means less damage, better detailing means less damage and more dependability. Certainly since the Christchurch earthquake in 2011 in New Zealand, the emphasis has been on better resilience. And generally avoid first and second mode torsion with better layouts for mid-rise and high-rise structures. Now, this is one of those things that as structural engineers we get brought up with as we start designing commercial sized buildings in particular, but it isn't really codified. And so there can be quite a lot of resistance to this approach of trying to make sure buildings are symmetrical and that they avoid first and second mode torsion. I'll talk a little bit more about that in an illustration later on. Mandalay, I took these photos off the internet because I didn't get into Mandalay after the earthquake. They all tend to show that some buildings had bottom story, soft story collapses, and that's seen very often around the world because of building layouts, because of lack of column strength hierarchies over beams, etc. So I guess I ask, what will the result of all of this experience be in terms of the development of earthquake code approaches and earthquake design practice? What can be controlled? What's difficult to control is what the size and location and depth and specifics of the earthquake will be. We see that with the comparison between Christchurch, Port Vila in Vanuatu, and Mandalay and Bangkok. But I'd like to say what I think we can control, and what we see time and time again is similar types of issues through a lack of what we now understand as good detailing. And I don't sit here claiming that New Zealand has the best approach to all of this. We have learned over the last 20 years from real earthquakes, and we would like to see that other people get the opportunity to learn as well. So into damage and detailing. Column damage. These three pictures are from Mandalay, from a site that we were asked to advise on from a distance. This column here, it's been pushed out because there's a stiff low wall here, which is effectively making this column critical zone where it wasn't expected to be. So that's pushed that column out and much higher shear forces than expected because the column's not effectively very tall. This is at the top of what I take to be a seismic frame and just will be a result of inability to drift. It could be even a gravity frame, but probably an inability to drift because of a lack of close-centered stirrups. And then this one, which really looks concerning, it's a large concrete column. You can see it's in an industrial facility, and so potentially under quite a bit of load by design, and it's lost all of its internal core concrete, and so really down to not having close enough centers in the stirrups. The bars have buckled, the core concrete has been lost, and that column really isn't much good for anything now. The floor above will be in catenary action, just hanging in there, as we say. You can see that right inside the column, the bars are tied well. So the layout of the bars and the layout and plan of the ties is quite good. You can see though that we don't have 135-degree hooks necessarily. So the hooks are not into the core. So if this had been at closer centers, there still would have been some issues of slippage of those ties because even though the core concrete would have begun to be, tried to be contained with the wide centers, that would have been lost, and then you no longer, even with a good hook inside the core, you no longer have core concrete to hook that into. and so that all comes apart too. But number one issue here is, as you can see, is the stirrups are not at close enough centers. Here's a column in Thailand, in Bangkok. And so despite the distance of the earthquake and the relatively low seismic accelerations, this column just hasn't been detailed well enough to deal with the axial forces, and it's gone in the location where the stirrups are small and widely spaced. So the bars have buckled. That means the column has lost height. There's been a pushing down. And you can see that would be very difficult to retrofit in terms of getting the existing column to work, because what do you do with those bars? Here's some observation of that column and its retrofit. So immediately they've put some formwork up and put some concrete around it. Question mark here is whether they've tried to jack the column back up, whether they've been able to put any reinforcing bars in there to take over from the buckled ones. And then they've tried to confine all of that with steel plate, which looks reasonable. My question in my mind is whether in that long side of the column, this plate is going to provide enough confinement, and possibly these holes can be used to drill through some ties to give intermediate confinement. I suspect these holes are rather for a post-grouting exercise starting from the bottom. Then you wonder about potentially, if the bars haven't been replaced, how the load transfers locally here from the steel outside into the column, because there's no bearing on the floor or beam above. Here's another way you might do it rather than steel. This is from a detail we've done to strengthen a building, an undamaged building in Wellington. And it's basically a concrete surround with a lot of bars put in the outside, and that amount of bars could be increased. And then very closely spaced ties epoxied into the existing column well enough to make sure, deep enough to make sure that even if things move around, those are well confined, and this acts as one column. Moving on, here's guidelines which have been established. This is the latest version, but they've been in process since the 1990s, and then got a lot of impetus after the Christchurch 2011 earthquake, which is usually the type of impetus needed to get industry supporting these things as well, and government, even in New Zealand. And these are called the Seismic Assessment of Existing Buildings Guidelines, Technical Guidelines for Engineering Assessments. They're available, I would say, to you, and they have some very useful things in them. I'm going to concentrate on reinforced concrete because I think that's probably best in the context. And these are the latest. What they've done in these guidelines is they've taken photos from the Christchurch earthquake on different elements of the buildings, and then explained what the weaknesses were by looking at original drawings where those were available, trying to firstly understand how to assess existing buildings of certain age and certain detailing, and then secondly to encourage better into the design code. So in this case, columns have had a shear failure, inadequate lap splicing, you can see there, but short and not well confined, and inadequate shear reinforcement in key zones. And so that's led to shear failure, and then a bit of a softening. Also, once that starts to happen, you then get a weak column, strong beam mechanism, which in the end can lead, if it goes far enough, and if perhaps here, if the shaking had been longer than 10 seconds of strong shaking, or 10 to 20 seconds, then this could have ended up being a side sway failure and a soft story collapse, as we saw in those Mandalay pictures. moving swiftly along. Here's a short column effect. The column is short, so it's already quite stiff relative to the beams and the rest of the building. So movement is concentrated there. It's made worse by stiff brick infills next to it, which makes the building think it's twice as wide and as a column and very stiff like a wall, acting like a wall. It gets a shear failure there and really falls apart. Likewise, similar here, short column effect. There were a number of examples of that in older buildings in Christchurch. This is due to, again, is due to poor confinement. You can see that's a very widely spaced column bars and lack of cross ties means that this has initiated with an axial failure and then quickly turned into a shear failure right through the column. This is clearly weak column, strong beam, the reverse of what capacity design tells us we would like to avoid soft story failures. And a little bit of short column here as well led to severe shear failure of the column, and which results in a loss of gravity load carrying capacity. Another example here, inadequate confinement and a lack of stirrups in the joint means that in the critical zone at the base of the column, plastic hinge zone, when the building movement becomes excessive, takes the column past yield, this is just blown apart and again starts to lose gravity load carrying capacity, which is the worst thing it can do. Beam column joints, typically in older buildings, we see either no stirrups, no recognition that there's a potential for shear failure through the joint. You can see it there. Or columns have been designed with stirrups just taken through the joint, but at the same centers. And so a lack of recognition that effects are concentrated in beam column joints. And then if you have old buildings with relatively small columns and deep beams, it gets very difficult to have enough space, even with hooked anchorages, to anchor beam flexure at the column face into the joint and node it there properly. So these are all problematic, mainly because of the size of the column, but also because of either a lack of hook anchor or hook anchors bent the wrong way, or in this case, attempting to lap, dealing with perhaps the joint anchorage, but attempting to lap the bars in the plastic hinge zone, which can lead to rapid unhinging of the joint as it rotates. So that was columns and frames. Wall damage. This is in Bangkok. Interestingly, it's not at the bottom of the building. It's partway up, maybe at 40% of the height, 30, 40%. So that shows secondary effects can be critical. This is the building plan, and it's not immediately obvious, even though we look at the short direction and we think distant earthquake, first fundamental period of the building would be in the soft direction, and we think soft direction will be the short direction. But when we look at the walls, the stiff walls are the orange and the red, but the walls designed for earthquake loading are the red ones, reinforced for earthquake loading. So when we look at this, we wonder actually whether the building wanted to shake in the long direction. However, the type of damage shown here, the buckling of these bars due to a lack of cross ties, the way these windows have buckled outwards and not sideways generally, tends to suggest that the building reacted in the short direction. And this orange wall, relatively thin, was apparently designed for gravity effects. That's it. That's the wall with the dotted line around it, which tends to suggest that this has just been overcompressed. It's tried to act as a flange in this direction on this wall because the building doesn't know that it hasn't been reinforced well. It feels as stiff as the red wall, so load goes into it. and then you get these buckling failures. That's a very difficult thing to fix in terms of how do you get that, how do you jack that up? You probably don't. How do you put something on that wall to replace the gravity load carrying capacity lost, and then how do you retrofit? This is damage inside the same building. Clearly went through a lot of movement, probably relatively lightweight on the internal partitions. Perhaps a wee bit of tilt here. And then this is at one end of the building, I understand. This looks like more of a shear failure through something that was stiff, but appears to be potentially brick in there. So again, stiff, but not necessarily that strong. These are from the New Zealand guidelines for assessing buildings, and mainly out of experience from Christchurch, and these photos are from Christchurch 2011. Inadequate longitudinal reinforcement ratio means that bars tend to fail. They fracture, and they fracture because all of the action occurs about one crack, rather than a fan of cracks that you would get if you had a higher axial ratio of reinforcing bars, which would spread out the effect and lead to more ductile action. Fracture of that bar definitely is brittle. Inadequate confinement and shear reinforcement in the walls, and so the reinforcing here is turning in here, but it's not cross-tied at the ends, and so high compression zone has meant that those bars have popped out, and a loss of shear capacity in the wall and buckling at the wall ends. Similar thing here. You can see where the wall turned a corner and had a flange. It wasn't well detailed. At the straight end, it wasn't too bad, but the longitudinal bars were anchored at the end and not in a confined zone, and so they popped out. And so a combination of compression failure and a little bit of buckling, but mainly these longitudinal bars popping out and no longer resisting shear, and therefore a shear failure in that wall. Here's some thinking about how that could be fixed. Seeing a little bit of this coming out of responses in Bangkok, where shear failures in hospital buildings have occurred, probably due to the sort of detailing we were just looking at. So you roughen the interface, the existing wall's the clear bit, and the shaded piece is a bandage. That could be done in steel as well. We've seen some examples of that, but it's possibly more convenient to do it in formed up concrete in terms of the ability to get bars and materials in place rather than moving big sheets of steel in. Hooks on the ends of the bar laps are a necessary thing, and they're part of our new code approach to try and avoid this, where a bar has a straight overlap and no cross ties, which means they tend to pop at those laps or at the ends, as we saw before. And so these overlaps have a 135-degree hook in the new piece around the new vertical bars, and then cross tying, which is important to stop the wall trying to come apart and to keep the horizontal bars acting as well as the compression zones. Either a straight cross tie, one end straight cross tie with a 135 hook offered through a hole right through the wall and then bent down. That's preferable because it gives you a right through tie. So it's not as dependent on the quality of this concrete. Or, as we've seen more often, bars epoxied in from each side. It's important to, if that's going to be the approach, to make sure those are into very competent core concrete, so that they will actually act when they need to. How am I going for time? Probably not too bad. This is another example of a wall in Christchurch where there were some unusual shapes and orientation of walls, which makes the performance hard to predict. There was some buckling at one end, and there was a loss of shear capacity and some crushing at the other end. So that's really a warning about not only detailing, but how walls are aligned with the building. This is an example of a wall in a very tall building, which wasn't really detailed properly for buckling. This had a small zone here that made sure that the shear worked. Anchorage was within confined concrete. That was good. But there wasn't enough resistance to buckling out of plane. And when that wall underwent probably higher compressions than it was designed for under earthquake action, that buckling happened. This type of detailing in the new code approaches would, and indeed in ACI modern approach, would assist with that. This is an example of a building strengthening we've done recently in Wellington, where we've put these boundary elements in, well cross-tied, tied along the length to the existing end columns, so that relative action is transferred, and then well epoxied into the existing wall. Now, it was seen as adequate to epoxy into the existing wall because all of the anti-buckling actions being done by this properly detailed reinforced zone here. Thinking about wall layouts, particularly from the Bangkok experience, the state audit tower, which unfortunately collapsed, was a 30-story tower. So similar to this, this isn't the plan of that, but similar, with quite a few core walls and quite a large core relative to the floor plan, which is, these are both to scale with each other, but very thin, 300, 400 thick walls even, 30-story building. Admittedly, this is a 52-story building, so some 20 stories more, but a wall layout that allows for better detailing, as we'll see here. So in this same two floors, in the core on the right, thin walls, lack of cross-tying, inability to really put good boundary elements in most of the locations, as you can see here, completely missing in the corners. Whereas here we've detailed this for boundary elements, and because many of these are separated by link beams, they've turned into column elements rather than wall elements, so they've been detailed as such. You see here in the long wall elements, the ends are detailed for boundary element, high compression at the ends under seismic action or indeed wind action, and then cross-tying through the intermediate zone. Now this applies to the plastic hinge zone, so the key ductile parts of the building. In the bottom, perhaps twice the length of the wall from the base and into the basement. And then in this case, in the case of this illustration, with an outrigger above, probably a length of wall of core above and below the outrigger, to make sure that concentrated actions here don't result in, well, they will result potentially in hinges from higher mode effects and concentrated actions in the outrigger, but they can be dealt with. The rotations can be dealt with, and the high flexural actions, if the detailing is good. So a hinge zone detailing there, ductile detailing, and down here. And then in between, I'll show you some potential detailing for that, more around making sure that any column elements with concentrated compressions can cope, and making sure that the horizontal shear steel in those walls is adequately anchored in confined concrete at the ends of the wall and cross-tied.
Engineer Wood, excuse
Hello.
me?
Yes.
Yeah, can I interrupt? So it will be appreciated if you can wrap up your presentation within a couple of minutes for the following Q&A. We have a limited time for closing the session.
Oh, okay.
So, yes.
I got started quite a bit later than expected, but
Oh, yeah.
but I'll rush through. So so these outrigger wall zones and vertical transfers here of columns and transfer diaphragm at the base, they all need to be designed for earthquake overstrength actions for a hierarchy of failure. I'll flick through this. This is similar to what I described on the boundary element detailing. there are requirements for length of boundary elements, localized column zones, and detailing each side of link zones. Right, this just shows in more detail and references the ACI clauses for minimum detailing, even in intermediate, moderate seismic zones like Bangkok, but much more important in places like Wellington and Mandalay. Here's a typical column element detailing. The ACI code, it should be noted, is about to go to New Zealand approach of a full hook each side and not allowing hit and miss hooking, 90-degree hooking into the cover concrete. So that's worth noting. That's sort of come about since this was drawn up. And this shows here with the red bars, just horizontal bars being anchored into confined concrete, not being taken to the end where they would be subject to cover loss. This is for outside the hinge zones, detailing each side of a link beam to make sure there's for localized high compressions, there's good confinement and anti-buckling reinforcement, and through the where only shear, good shear anchoring in the ends of the walls is required, some ideas about how that can be achieved. Righto, low strength solid infills cause damage. Typically they're not designed for as an earthquake load path or for the stiffer response that they give. So people will design the frame and then they won't think about these in contact infills, which end up stiffening the structure and attracting higher seismic loads and causing damage, particularly where they're partial. We saw that with that picture from Mandalay, where you have a partial height infill and strutting there. You can get pressure points on the columns, the effective shortening of the column and shear failure, and some pounding as the frame goes back and forth against that. So either separate the infills from the frame with localized detailing, which we prefer in New Zealand, given our high seismicity, so that the frame as designed can respond in a ductile fashion, or design for stiffer response and work out ties for the struts, the diagonal struts through the infills. This is from Vanuatu. It shows, remember, 15 seconds of strong shaking meant that this building, all of these infills, unreinforced, largely in many cases unfilled, were stiff, but almost no strength. And so they went straight away, bang. But the severe shaking had dissipated by the time those all popped. And so the frame looks really good. And it's very misleading to my mind, because likely if this shaking had been another 15 seconds or 20 seconds, those frames would have acted as frames rather than being infilled, and then you would have seen significant damage at the top and bottom of these columns potentially. There's an example of where that did happen. So this fell apart. This looks as though, this picture makes it look as though there's reinforcing in there. It's not. It's the cells between the blocks, in some cases unfilled. So that's sheared. There haven't been probably so many of those at that lower level of the building, so those have sheared quickly, and then the frame has had to do the job, and that's very close to a bottom story, soft story failure. Probably another 15-20 seconds of shaking and that building's going over. Just a very quick building layout discussion, which I think's illustrative. This is the building that I showed before, the tragic loss of life. And this is a layout. So the black and the blue are the existing building. Core wall offset, very small core wall here. So asymmetry from left to right. So while the mass center of the building's in the middle, the shear center's over here towards the right. And that just gets worse and worse as the building twists around. If the shaking's in that direction, it appears as though the main shaking was probably the other way in terms of where the origin of the earth shaking was. However, There were no ties through here, and there were no transverse tie beams. So you had a series of gravity beams and concrete floor spanning, and insufficient tie of the shear wall across, and nothing to help those columns when the building starts going left to right. And so all of those things meant that the poorly reinforced columns just couldn't cope with the rotations, and the building rapidly pulled away from its core, and therefore it collapsed in on itself for a total disproportionate collapse. In summary, in terms of detailing, I think just a couple of things that I've noticed: various earthquakes, confinement is key. Don't underestimate it. Whether the codes tell you to confine or not, be a structural engineer and think about where those areas of high compression will be in particular, or yielding, and provide, so flexural yielding or high compression, and provide closer stirrup centers. If you think they should be closer than what your codes say, put them in. The cost of that is really relatively small. And then properly anchored tension ties in the building plan. If I go back to that, those ties across the building really would have made a difference to how that building responded together, kept it together with its lateral elements. And if you're going to anchor things, or you're going to retrofit by drilling into existing concrete, they have to be into properly confined concrete. There's no point in anchoring into concrete that is cover concrete or that can burst, because it's inadequately confined. In terms of building effects, lower drifts means less damage, but consider the site. Soft buildings on soft soil leads to higher damage. We saw that even with the distance of the earthquake from Bangkok. Tall, soft buildings, typically designed quite softly in Bangkok on very soft soils. Likewise, stiff buildings on stiff ground can lead to higher earthquake loading. So there's a bit of a trade-off there. That's something to think about. Better detailing definitely means less damage. We see that time and time again. Plan symmetry. Avoid first and second mode torsion by making lateral elements in each direction of a building symmetrical in plan at least. And then, as I illustrated with the tall building, a proper understanding of design hierarchy. Which are the elements that, if they fail, will lead to building collapse? Those need extra protection, both in terms of the loading they're designed for and the way they're detailed. Have we got time for a couple more slides on, very quickly, on low damage technology, or is that of less interest? I'm seeing a nod. We'll just go ahead. This is a building, 14-story concrete moment frame building in Wellington, which not damaged, but when assessed is well below the code levels of capacity required. We've put fluid viscous dampers into this building to limit its drift from something like 3 or 4% down to less than 1%, which provides both frame protection and protection to the hollow core floor system, which unfortunately we've experienced in New Zealand. You don't use them typically overseas, but we've found that they, under high frame rotations, they tend to break at the ends and fall off. So the main idea here was to stiffen the building. Sorry, not stiffen the building, to soften the building, to reduce the building displacement while not changing the overall frame stiffness. And so that means damping. And the dampers go a fair way up the building because the hollow core floor has a very thin 65mm overlay as a diaphragm. And so to reduce floor accelerations and reduce the amount of diaphragm strengthening, we put more dampers further up the height of the building. Base isolation is another key low damage design method. That's reasonably well known. I won't talk about that now, given our lack of time. There's a volume that came out of the Christchurch earthquake reports, which talks about other low damage design methods used in New Zealand, which may be of interest to people if they can get hold of that, volume 3. This was just to explain base isolation. I'll assume that you understand that and go past it. And this just shows the difference between base isolation and damping. So base isolation is a period shift, mainly from short period to around 2.5 seconds to allow a reduction in the spectral response. That's what base isolators do for you. Fluid viscous damping is direct damping. It doesn't change the building stiffness, but it brings the design spectrum down significantly, both in terms of acceleration and displacement. Thank you very much. Hope that was of some interest.
Okay, thanks a lot, Engineer Wood, and my apology for my abrupt disappearance due to my laptop battery issue. And we already, the time for supposed to close the session has been already passed, but I think it will be still available for taking a couple of questions from the audience. So if you have a quick question, we can take it 1 or 2. So please use the chat window and upload your question. And please keep in mind that it should be a quick one. Okay, the questions can go to the all of the presenters, which has been made during I mean within this sessions, except the Professor Imran. Okay, then I think yeah, we don't have any more questions to the presenters today, and I think it's time for closing the session today. I would appreciate your participations again. Okay, yeah, that'll be good. If you can share your email address, I mean the presenters, and that'll be helpful for the audience to give you the questions if they have after this this webinar.
Close that session, and we kindly announce the one session for next week.
Okay, thanks. Very
Thank you.
good.
We are arranging the session 5 for ACECC knowledge exchange among ACECC members in response to the 2025 Myanmar earthquake. And
So okay, so when is it?
it will be on 8th of October next week.
Okay.
Friday. So
Right.
Wednesday, same time, same venue, in person or online, hybrid system.
Okay, thanks a lot.
There are 4 executives from FedMesh will present about their experience in earthquakes and rehabilitation process, and also their future plans. So come and join. We will announce all this seminar arrangement. We will announce in our as usual ways, social media. So you can come and join next week. Thank you.
Okay, thanks a lot.
Thank you, sir.
Okay. Okay, so I would appreciate once again for your participation during your business schedule, and hope to enjoy the rest of the session, which is coming after this one. Okay, thanks a lot. Have a good evening and a good afternoon, everyone.
Thank you.
Okay. Thank you.
Thank
Bye, everyone. Thank you.
you. Reading from FMES. Thank you very much.
All of us.
You are speakers and moderators.